This is work that I've done in collaboration with the UW and Body Shop, so Fabio Governado, Allison Brooks, Tom Quinn, and also with Piero McDowell. To begin with, I wanted to introduce to you guys the new updated gasoline, which is now called Changa. It stands for Charm and Body Gravity Solver. And it's a massively parallel SPH code, and it includes supernova feedback, which creates realistic outflow. So this is a typical blast wave supernova feedback where energy is injected into the surrounding ISM, cooling is shut off, and that results in outflows in the halos that I'll be talking about. Our star formation is linked to shielded gas. And what's cool, new, and improved in the runs that I will be talking about today is the implementation of early stellar feedback. And what I would like to emphasize on this slide is that we have a new SPH implementation for hydrodynamics and diffusion that passes all the tests outlined in Aders et al. 2007, and it resolves all the issues with the Kelvin-Helmholtz instabilities and the cold-hot gas interface. So a little bit more about Changa scaling. What we have here are a number of cores on the x-axis, time on the y-axis. I'd like to draw your attention to the red line, which is perfect scaling. And even at hundreds of thousands of cores, Changa achieves 50% parallel efficiency. And so when we say massively parallel, we really mean it. And this is really cool. It has to do with the Charm++ load balancing that's implemented in the code. So now on to some science. I will be presenting to you initial results on a run we call the 40 Thieves. And the reason it has such an infamous name is because I was given these initial conditions as a little tiny grad student, and now I'm a postdoc, and I finally got them to run, and that's all because of Changa. And so because they're so infamous, they got an infamous name, the 40 Thieves. So it's a cosmological sheet of dwarf galaxies with an effective resolution of 4096 cubed, a gravity resolution of 60 parsecs, and an SPH resolution that goes all the way down to 6 parsecs. I was hoping that they would be at a redshift of 0 for this conference, but unfortunately that did not happen, and so they are currently at a redshift of 0.4, and I hope they'll be done by Friday. Cross your fingers for me. And as I mentioned before, these simulations implement a recipe for early stellar feedback. And so essentially we are modeling the radiation pressure that drives winds out of massive star clusters. And what's going on is that a certain fraction of the energy from type 2 supernovae is injected at a constant rate from the formation of a star particle to its first type 2 supernovae. And we don't turn off radiative cooling because stellar photons do not couple efficiently to the stellar ISM. And so essentially what's going on here is there's an isotropic thermal pressure that provides pressure support and gas heating into the gas. So the simulation so far, we form about 10 halos that form stars, and I've shown you the first 7 here. They're in that interesting range of mass that was mentioned in the previous talk. So they range from on the order of 10 to the 10 solar masses down to a few times 10 to the 8 solar masses in virial mass. And you can see the corresponding stellar mass and gas masses in addition to the Vmax for these halos as of Z equals 0.4. And another thing that I wanted to point out on this slide is we form quite a few halos at a few times 10 to the 9. But we form quite a large dynamic range, about an order of magnitude in stellar mass. So this highlights the stochasticity of the star formation in these halos. So to give you guys some context to some plots that I'll be presenting in a few slides, I wanted to bring up a few plots from Governado et al. 2014. So in this paper, he presents a run called the G5 run. And this run has the same resolution and the same physics as the 40 Thieves. And he, in this plot, looks at the cumulative star formation histories for that specific dwarf in his paper. And what he shows is a comparison to the local group and angst dwarf irregulars and dwarf galaxies. And with the correct apertures, the G5 run matches the cumulative star formation histories for these dwarfs. I guess, are observations. The black line is without any sort of aperture correction, and the dashed lines are with varying apertures. And what you can see is good agreement between the cumulative star formation histories. So last night, I thought I would look at this for the 40 Thieves. And so this is what I'm calling a May last night plot. So that this is very hot off the presses. And I don't think, I haven't even had a chance to send this around to the group yet. So you're seeing very new stuff. So again, it's a cumulative star formation history. And the blue, red, and it looks like blue on this screen, are the simulated dwarfs. And the purple is an average local group dwarf irregular that I got from Dan Wise's data. And so far, for the first 3 most massive halos in the 40 Thieves sample, we show good agreement in the cumulative star formation histories. And what I'd like to point out is that I didn't get a chance to apply the same aperture corrections as in Governado et al. 2014. So I predict that this most massive one will look a little bit better once I apply those aperture corrections. So no simulation talk is complete without a movie. So this is a movie of a random halo that I zoomed in on, and it's gas density. And I call it the little galaxy that could because just by chance I zoomed in on a galaxy that ends up blowing itself apart. So we're only going to watch the first few baby years of this galaxy, and it's just supposed to be a little bit of eye candy. So again, the brighter regions are the more dense gas regions. So on this busy slide, I have some star formation histories. And in the top plot, these are the star formation histories from Governado et al. 2014. And so the G5 run is the one that is most similar to the 40 Thieves and includes the early stellar feedback. And so what you can see is that the early stellar feedback tends to lower the star formation rate at early times. And just for comparison, down here I made some star formation histories for 2 of the halos in the 40 Thieves. And again, we see the same general trend. We're forming stars early on, and it's relatively bursty. And what I'd like to point out is Halo 2 is actually going through a little merger here at 10 gig years, which is why it has this big burst at the end. What I'm most interested in is the stellar mass-halo mass relationship. So in my 2013 paper, I looked at our previous generation of simulations and looked at the log halo mass versus log stellar mass and compared it to Moster et al. 2012 abundance matching relationship. And so the black filled and open circles are from that analysis. I ran the first 5 halos of the 40 Thieves through that analysis pipeline, and here they are on the stellar mass-halo mass relationship in red. So this is actually 2 points right on top. And to put this in a broader context, again, we're looking at stellar mass versus halo mass. And this plot contains many different stellar mass-halo mass relationships, including that by Jaeger and Kimmel, some from Peter Beiruzzi, and the Tully-Fisher results from Sarah Miller. And the triangles are from a 2013 paper, some of the more massive halos. And there's a simulation from Phil Hawkins. And then on top, I have highlighted the first 5 halos of the 40 Thieves in the broader context of all of the different stellar mass-halo mass relationships. And so what I'd like to say here is that they are probing this range of mass for kind of the derived abundance matching, and even the Tully-Fisher stuff stops having a ton of data. So it'll be really interesting to see what happens in these low mass range with respect to the ratio of stellar mass to halo mass. And I'm also very interested in seeing the effect of early stellar feedback on the redshift evolution of the stellar mass-halo mass relationship. So that's the direction that I'm going in studying the 40 Thieves. So there's lots of science that we can do with a large cosmological, very high resolution simulation of many dwarf galaxies on the order of 10. So I've mentioned the redshift evolution of the stellar mass-halo mass, or low And the red points are the simulations circa 2013 before the implementation of Changa. So we probe quite a large range in mass. And then in the lime green, we have the first 3 halos of the 40 thieves plotted on top. So we're making very reasonable H1 masses. And I hoped to make a baryon fraction plot, but I didn't quite have enough time. Something that Fabio is very interested in using this suite of simulations to study is the disk thicknesses without early stellar feedback in these systems. And something that is quite opportune and synergistic with another project that our group is doing is studying the Lyman alpha escape fractions. So our group is also running a large volume, which we've nicknamed the Vulcan. And within the Vulcan, we form a lot of dwarf galaxies. So my collaborator, Lauren Anderson, is actually in collaboration with Allison Brooks and Brian Sayana, is looking at the Lyman alpha escape fractions for these dwarf galaxies. So what they have found, their preliminary results are that if you look at star formation history and you compare it to how the Lyman alpha escape fraction changes with time in very early redshifts, you find that the shapes end up mirroring each other. So the yellow is the escape fraction and the white is the star formation history. And so what they need is high resolution in order to study this in depth. So one of the big criticisms that they get is that, okay, you have a lot of dwarfs and you get a statistical sample in your volume, but do you have a high enough resolution to actually study this? And so that's where the 40 thieves comes in, because they will have high enough resolution to be able to study this and convince people that this correlation is actually true. And in addition to that, and this is near and dear to Fabio's part as well, is to study non-CDM physics in these dwarfs. So in addition to the run that I presented here, we have run the 40 thieves with different dark matter physics. And so what I'm showing here is a result from Governado et al. 2014, where he looked at, as a function of time, the dark matter profile slope at 500 parsecs. And for 3 different dwarf galaxies, one that includes more dark matter physics. And this is only for one dwarf galaxy, so it'll be very interesting to see what happens in a sample of 10 galaxies with similar resolution and similar physics. So to conclude, the 40 thieves will be an excellent data set for new science. I specifically hope to study the evolution of the stellar mass halo-mass relationship and extend it down to very low halo masses. I'm also going to look into the gas fractions and baryon fractions and study them at these very low halo masses as well. I've mentioned that the group is very interested in studying Lyman alpha escape fractions, and that we'll have some interesting results on dark matter physics in the future. Thank you. Sorry.
Medium high.
Okay.
But simply everybody is choose that.
You have a trick, and like everybody in SBA simulations, the trick is that you have
No, she's having trouble understanding you.
Okay,
the issue is what's the resolution of your gas?
Go on.
I'm sorry. I
What's the
just can't
resolution
hear.
of your gas?
The resolution of my gas physics.
You've got gravitational forces, and I think you have much better quote unquote resolution in your gas.
Let's put it down to 10%. And that seems to be what the Greek everybody in SBA should do it. And that facilitates feedback. So once you have a study and 5 particles or 6 particles resolution, up to 6, you don't have a lot of blending happening, so you cannot derive. And that was only after that you start to ready.
Right.
That's also the Greek and also the increases, there's nothing big. So why you do it? You're not saving any city, you're just punching up.
I mean, I would say that all the results that I present are above, I smooth over above the
No,
gravitational.
but when the simulation runs,
Yes.
it has that gap between hydrodynamics and such pressure gradient and the force of gradient. Doesn't matter how you choose it after.
I'd say sure you're above it.
Well, he's always the data
So I would say, so the stuff I showed is also like that for two of the runs. So for one of the runs, for just this reason, we actually ran it with exactly the same force resolution for the smoothing on the gas and the dark matter. And that was the intermediate run that I didn't talk about. So it doesn't produce drastically different. I was worried about exactly the same thing. It doesn't produce drastically different stuff, at least in the simulations that I
Why
showed.
do the drastic results factor of simulated physics? And why doing tricks that you do it right away?
I think it's because people are obsessed with resolving the ISM and they don't care so much about the dynamics. They want to get there. I mean, that's the motivation.
No issues, no opinion.
Maybe puzzled that I missed something, but in the table you showed at the very beginning with your halo masses and your stellar masses, it seemed to me that the halo masses were the same as what James was talking about, but your stellar masses were drastically different.
Yes.
Any comment on that?
I think they're too high. I think
No, it's not.
I would say if the local group is weird, then there's nothing wrong with that. But if you think the local group is at all representative, that's going to be hard.
And like I said, the simulation is still running, and this is literally the first look I took at it. So you're seeing as it runs results, and so I'm gonna have to spend a little time with the 40Gs. But this is kind of the first time it's actually working. So I'm just showing you.
You still have till Friday.
Exactly. Come and talk to me on Friday when it's in CF0.
Okay, thank you very much for that talk.